this is the GitHub Actions for Scientific Data Workflow tutorial. And we're grateful to the RSE organizers to allow us to present this tutorial, and also facilitating the option to do it online and reach people that may not be able to go to New Mexico, which is a beautiful place at this time of the year. I used to live there, but I won't be going, but I'm still happy that I can actually kind of be part of the community and present. And the tutorial today is going to be presented by me. I'm Valentina Staneva and work at the eScience Institute at the University of Washington. And Quinn Brancher, who can introduce himself. He's on the call.
Sure. Hi. Yeah, I'm Quinn Brancher. I'm a PhD student in civil and environmental engineering at the University of Washington.
And this is also joint work with Scott Henderson, who is also working at the eScience Institute with us. And he helped contribute to developing some of the materials, but he's right now in Germany, so it's a late time for him. And as I said earlier, we have a bunch of links, and I'll pause for a little bit so that to make sure that everybody gets their links handy, because we will be using these slides during the tutorial, but we also have a GitHub repository, and we also have some lesson content that you can kind of use to refer to it on the site. And as I said, there is a DI survey that you can start filling out right away. And we'll really appreciate it if you can fill this out, because that kind of helps us understand who we are serving and who we are not serving through these tutorials. And I'll also say that the tutorial will be a combination of these slides and actual work on GitHub. And it's a 3-hour tutorial, so we don't want to talk for all the 3 hours. So the idea is that it's interactive and you actually try and do things on your own in your own GitHub account, and so that you can kind of get your hands on the GitHub Actions. And for that, all you need is actually a GitHub account. You don't really have to preset anything, and we'll give you some instruction how to proceed. But if for some reason you don't have a GitHub account, you can actually make one pretty quickly. We don't have a link here, but I think you can figure it out if you Google that. So yeah, we assume some general understanding of GitHub, so that would help. But in general, it's not really strictly necessary. And we will also, because it's a long tutorial, we will be happy if people ask questions as we go. You can ask them in the chat. You can just unmute yourself and ask questions. You can raise your hand. You can take the approach you prefer best. And we have this chat icon that here and there will kind of have a few prompts for you so that you can answer in the chat, so that we can kind of discuss things. And a little bit more about ourselves. So who we are. I personally am a data scientist, research scientist, and I work at a data science institute on campus. My background is in math, and my research has been particularly on image processing, time series analysis, and machine learning. I work at the eScience Institute with people from very different domains, and I like a lot of signal processing, image processing kind of applications. That led me to also start working a lot on oceanography applications, despite me not having any training in oceanography. And some of the examples that we'll share are actually from the oceanography domain. And as part of my job, I also spend a lot of time doing education, training people in data science, open source software, and so on. And that's why, as occasionally, I also enjoy preparing tutorials and teaching some topics that I have encountered that seem useful. And Quinn can introduce himself more in depth.
Sure. Yeah, I'm in my 4th year at the University of Washington in my PhD program. And my work is mostly focused on developing methods for radar remote sensing to measure surface processes in Arctic and alpine environments, particularly focused on things like glacier mass balance, landslide movement, and seasonal snow. And I got exposure to this project through a winter kind of course or program, I should say, that I did with Scott Henderson, where we basically needed to find sort of the appropriate tool to do what we wanted to do and landed on GitHub Actions. So that's sort of how I ended up here.
Thank you, Quinn. So yeah, like back to what this tutorial is about and why we're doing it. The first important thing is that, as you see, we are research scientists, data scientists, hackers, developers. We're not Microsoft employees. GitHub Action is part of GitHub, and GitHub is part of, it's kind of owned by Microsoft. But our exposure to GitHub Action was through our own work and our applications, trying to do our science and trying to develop our workflows. And then we kind of realized that we could use GitHub Actions for this. And kind of through this experience, we discovered that there are a lot of good use cases of GitHub Actions. And the reason for this tutorial is that we also realized that those uses of GitHub Actions may not be popular to people. And a lot of times people do hear about GitHub Actions. The first time is through software development and through setting up some sort of a package, kind of packaging some software and seeing some continuous integration or continuous delivery pipeline. Most importantly, usually people see it in the form of testing, automating tests. And we think that there can be a lot beyond that, and that's the purpose of this tutorial. So in a sense, we will not focus on the more typical cases. And some examples that we'll have is, for example, continuous update of data visualizations, or how to process free data, how to process data for free on 60 machines. And kind of one of the goals is to also really just use this as an opportunity to think of new unexplored ways of using GitHub Actions, maybe for other people's research. And it is a little bit of invitation to collaboratively share the use cases and also discuss the limitations, given that we're not saying that people should use GitHub Actions for everything, but we will just discuss what maybe people can use them for. And to that, this is kind of who we are and what we are kind of planning for this tutorial, but we thought maybe you folks can also a little bit share where you are and why you joined. And the idea of this is that just get a sense of who is on the call. And that's why we came up with these 3 categories. Like the tutorial is designed to be for people to who are even new to GitHub Actions, and they will learn what GitHub Action is about. We'll spend quite a lot of time explaining that. But we suspect that maybe some people have seen some other uses of GitHub Actions and have joined to learn about new use cases. But possibly also some people who have joined already know a lot more about GitHub Actions than us. And we'll be happy if you help us in this tutorial because we don't know everything. So feel free to share the icon that corresponds to you. And this is just kind of to see who is around and get you started on the chat so that you know where to type. And thank you for sharing the icons. Okay, we have some computers and books, so I think that's a good place to be. Here's the plan. So we'll start with overview of GitHub Actions and workflows. We will go through the first GitHub action workflow. As we said, we want everybody to get started. So we will start very simple with an example of setting up a scientific Python environment. This tutorial the examples in the tutorial are in Python. Forgive us if this is not the language you use, but that's not a problem. Like GitHub Actions work with any language, and we don't think the language matters. I think you'll get an idea even if you're not using Python, but you're using some other language. We'll kind of explain more the use cases and their typical use cases in kind of in just building scientific software and building workflows. So I think as long as you can read some code, you'll be fine. And we'll be curious to hear if people have using other languages, what those languages are. So yeah, the examples are in Python, but they're written already, so you don't really have to write code. You just need to run stuff. So we have one example, which is showing how to set up a scheduled deployment of some algorithm to a real-time stream. We'll use the example from oceanography for that. And then we'll discuss several different ways to export results from this workflow, which can apply to any sort of workflow you do, and think about how you can actually get the results from that. Then we'll have a break, and then we'll dive more in large-scale data processing. We'll use a satellite imaging example for that. But again, you can think about how that applies to your use case and how you can use it with your big data. And then we'll go back to a few more examples of what else can we do. And one of the things that we have discovered is, sometimes you do your science, but you don't share it. So we thought, well, maybe we can automate the process and you can share your results on a web page. And we will discuss also some ideas of what if we want to work together, develop models together, and kind of compare the results. And most probably we'll run out a little bit of time for that. But we can just discuss the use case, even if we don't dive into the details. So that's the plan. We don't know how it goes in terms of time. So please stop us, ask questions. We don't have to stick to any specific timeline as long as we go through the topics. And we have some learning objectives that are here just to keep in mind what we hope to achieve. So we want everybody to understand the difference between GitHub Actions and workflows. And there's understand the language, but also understand the role in the typical software development cycle. We want people to be able to trigger GitHub Action workflows on their own after the tutorial. And most importantly, we want them to be able to decide what kind of workflow they may need for their use case. And we want people to be able to export and visualize the results so that they can actually get out of GitHub what they have produced. And we also want people to be able to build a process to process a large data set. So these are kind of our main goals. And most importantly, we want people to leave with some ideas of how they can integrate GitHub Actions in their own work. Or maybe they can leave with the idea that they don't need GitHub Actions for their own work because maybe their case is very specific and it doesn't work. That's fine too. Okay, so we have two scientific use cases, which we find very interesting because they're from our own research. We hope you find them interesting too. But if not, think about how your use case is similar to that use case and just try to translate. So one of them is real-time processing and visualization of an audience stream from a hydrophone. These hydrophones are here. We're in Seattle, and they're kind of close to where we live. And in Seattle, we also care a lot about the conservation of orcas. And we have built this framework, this kind of network of hydrophones, which can monitor the sound in the ocean. And this website called Orca Sound, one can go and listen live to the sounds of the ocean. But the interesting thing is that there is also data that is collected in real time, and we will discuss how we can process and visualize this data with GitHub Actions for free. And Quinn can share a little bit about his use case.
Sure. Yeah, we're going to go through a batch computing use case where we process many different pairs of satellite images and cross-correlate them to measure glacier velocity and make measurements that have applications for glaciers providing water and also sea level rise.
Thank you, Quinn. Okay, so let's get started. What are GitHub Actions? I have this statement, which I copied from the GitHub Actions website. GitHub Actions is a continuous integration and continuous delivery platform that allows you to automate your build, test, and deployment pipeline. That's what I consider to be the typical use case of GitHub Actions. And usually people encounter it while building software. And they can use GitHub Actions for their testing, for release, for documentation building, and so on. And there are other platforms to do that. GitHub Action is not the only one. It's kind of nice now that it works with GitHub, but some people use different platforms. And usually, if you look at any open source package, like for example, here we have scikit-learn, you see a lot of these icons, and they usually indicate some sort of continuous integration service running. And some of these are GitHub Actions, and some of these are other services. And as we said, the goal is not to dive deep into those, but we still thought to share a few of the examples that are already existing. And we think the best way to learn these uses of GitHub Actions is kind of through the process, like kind of a different tutorial in which you focus specifically on let's say building a package in Python, and you go through all the steps, how to set up like style checking, testing, and building. And here we have shared a few of the most common ones that people use for Python. At least that's what I think. As I said, style checking, testing, coverage report, documentation building through read the docs, package building, publishing on piping. So, and for those, I believe also it's really worth it to sit down and go through every little detail of this kind of each of these examples, because there's a lot of details you have to go through. But we'll talk a little bit more about GitHub Actions in general. And here's another definition of GitHub Actions, kind of what more are GitHub Actions? A platform to run any not too complex workflow in a virtual environment and integrate with GitHub. So this view is rather different, right? This is kind of any workflow. It doesn't need to be building a package. So anything you're trying to do, can it run on GitHub Actions? Well, I don't know, but in a way, if you have something that you can script it through you can have some scripts, you can have some commands, things like that, most probably you can run on GitHub Actions. If it doesn't take incredibly long time and it doesn't require incredibly complex system to run. And the reason is that a workflow usually consists of kind of the idea that you're gonna run several jobs in the workflow. You can have job 1, job 2, and you run things in some sort of sequence. And the workflow can have, as I said, it can just have some sort of Linux commands, but it can have scripts, and it can have also action, which is An action in this case is some sort of cooked operation that you can run. And I'll say a little bit more about it. But in a way, a lot of goes into this category, right? Because if we can run things on the command line, we can do a lot of stuff. And the idea is that these steps can be specified through a YAML file, like a configuration file. And the configuration file will also specify other things, not only what you run, but when you run it, the event on which you run it. And in the context of GitHub Actions, a lot of the events can be derived from GitHub. Some operations on a GitHub repository, like pull request, push. But it can be something else. It can be just a schedule. So things can run on a schedule, and that's where we can use the power to automate things. Or we can just run things manually. So on the other hand, we also have what's called runners. And runners are basically computers on which things run. And those computers can be provided for free by GitHub, so we don't have to have our own computers. But we need to specify sort of what is the operating system of these runners, and you can have any operating system and maybe some details of the environment. So on the other hand, we also have, for GitHub Actions, it's kind of like a whole platform. So we also have this option to monitor what's going on. And that's why it's nice, because we can run things on the command line, but it's nice to be able to have this view of where our workflow is at some point. And we can also store results in what's called artifacts. We'll talk a little bit more about that. But in a sense, we can export the results. And here we have also this marketplace, which I'll go to the website to kind of try to explain what it is. It's kind of like we also can have a community which builds these actions, which is things that many of us need to run. Like, for example, we want to install Python, and we don't want to go through writing our own scripts how to set up Python, but we can have an action, which, as I said, is a packaged version of some code that sets up Python for us. So in the end, it's going to be just one line, set up Python. So that's kind of the idea, that sometimes you have steps that we all are using, so why not have one liner for it? And at the same time, we can also have our own workflow converted to a one-liner. If we're going to be using it very often in our scientific community, why not make an action for it and kind of automate the process? So these are all the pieces, and we can dive a little bit more into them. Okay, so language, disambiguation. GitHub Actions is the whole platform. On the other hand, GitHub Actions consists of workflows and actions. It's confusing. I don't know why they decided on this language, but it's fine. So let's be clear what is the difference. So the workflows can run individual actions. As in this example here, the workflow can run one action inside. But also steps of a workflow can be converted to an action. So it can go both ways. On the other hand, actions are packaged. As I showed in that marketplace, we can have a Python setup, R setup, things like that. And some of them are actually provided by GitHub, but some of them are provided by the community. So I guess the ones from GitHub, people can have common agreement that they'll use them. And the ones from the community, people can, in fact, vote for each other and like each other's actions and decide if they're good product to use. So the runners are the computers on which we're running things. And in the end, behind the scenes, it's some virtual computing environment. Now that this is owned by Microsoft, those are most probably some Azure machines behind the scenes. But from our point of view is like we can use some stuff for free, and that's most important to us researchers who don't have a lot of money. So we can have any operating system, and we can specify the operating system just by basically saying something like runs on Ubuntu latest, or you can specify a version you want. You can get, so like on the right-hand side, it's some example of what do they provide. And I think here we can see that we can actually use these machines for some actual real applications, because as we can see, you can get 16 gigs of RAM, which is pretty good. I think in the past it was 8, and even with that, you could do some interesting stuff. But with 16, it's even better, and 16 or 14. If one needs more, they can actually get larger runners with a team, an enterprise account, and many universities and maybe some, I don't know whether it's some other nonprofit entities can actually get the team account or enterprise account. So that's something to investigate, that maybe we can even get more than these free versions. For sure, in University of Washington, we can get enterprise, I think. And you can also host your own runners. So basically use the same system, but link to your computers. So that provides quite a lot of options. And in terms of events that can trigger the workflows, this picture it's a little bit hard to see, but I stole it from their website. The idea is that you can use a lot of the GitHub events to start a workflow. In our experience, we either use something popular like push, pull request, issue, something like that. We can use schedule times or manual workflow dispatch. There's way more options, but maybe it's not a typical use case, but people can be creative, how to get those started. And here's a little bit of overview how those events can be specified in the configuration files. For example, we can just say on and specify whether it wants something to run on push, on pull request, or workflow dispatch. Workflow dispatch means that you're just gonna get a button and you're gonna run this manually. So that's the term, manual. And you can specify whether you wanna run something on your main branch or a different branch. On the right-hand side, you also see that you can run things on a schedule. And that's kind of interesting because that goes way beyond these typical GitHub events, because you can start automating things, and schedules use typical cron specification, which basically you have to specify the minute, the hour, like every 5:30. Every time at 5:30, run something. And this doesn't specify the day of the month or the month, so it means every day. And this specifies the day of the week, so this means Monday and Wednesday. But you can read the documentation in case you need to set up. There's a lot more options how you can configure this. And one thing is just to know that they're not that exact. So if you want a specific minute, it may not work out. You may need to use something better for that, but it's good enough. Okay, before I dive further, I'll just stop for a few seconds, and I want to see if there are any questions, conceptual questions, based on a lot of things that I said. Okay, I think there are some comments, but I was not looking at them because I couldn't see them. Thanks for sharing the R actions. Yeah, I would love to hear if people are using other languages too. I saw there's a Julia setup. I don't know if you, most probably if you also your code to run some Fortran, most probably you can make it work too. I haven't tried that. So yeah, any other questions just generally on the topics? If not, we can look at the first example. And the way I'll do it, first I'll talk a little bit through it, and then after that, you folks all will dive and run it yourself. But let me just first kind of demo it, and then you can dive in. So a little bit on the organization. So our first example is just running a setup for Python, to set up a Python environment and install some packages. The way GitHub Actions work is that everything gets stored in GitHub/workflows, and the configuration I mentioned about goes into a YAML file. So this is an example of a YAML file. And in the context of our repo, you will find everything on the workflows. So let me just show you so that you know how things will look like. So this is our repo that we'll use. And we can go to GitHub workflows, and you see a bunch of workflows that we have prepared. And we have Python env workflow, which is a short YAML text file. So that's kind of where you specify things. And what do we specify in this case? Well, we specify how to run it. As I said, this is the manual version, workflow dispatch. And this name is going to give us a nickname for our workflow, so later we'll be able to find it. So it doesn't matter what the name is, but depending on what you put here, you will use it to find it in the list of workflows. And we set up the operating system, as I mentioned. In this case, it's Ubuntu. And we set up Python. As I said, it's one-liner to set up Python. So that's kind of nice. And they usually have these versions, and the idea is to use the latest version. And you can check, sometimes they get out of date. And then we will just run a command. So in this case, if you do run, you can really run a kind of like a command line command. In this case, the command line command is going to install two libraries, Matplotlib for visualization and SciPy for scientific computing. So that's all, kind of like, but it's the fundamental step to get started with any language. You can set up some different language, and most probably you'll need to install packages. And we think that this workflow is important because we often, when we work, if we are not using GitHub Actions or anything, we will never sit down and identify which packages we need until we start writing software package. But this will force us that we start from zero, right? We start from a clean Ubuntu system. So in a way, we also think that GitHub Actions help us make our code reproducible, even if we're not at a stage of writing a software package, which is good because we often have scripts that can get messy. Okay, so this is one example. And for those who have been using Python, they'll ask, well, here you used pip install packages. Can we use Conda? Yes, we can use Conda. You can use some other ways to install packages. You have to find the corresponding action for this. And in this case, somebody has made a Conda incubator, set up mini Conda action. This Conda incubator is the name of who has created the action. Set up mini Conda is the actual name of the action. If it's just actions, means it comes from GitHub, their standard list of actions. If it's something else, it's community setup, but that's fine because if many people are using it, it's fine. So you specify your miniconda version and you install some packages again. Same thing in the end, you have command install. So that's kind of the idea. I made an example in R, but we don't have the example in R as a YAML file. If you're using R, you can create your own, but I kind of wanted to send a message. It doesn't matter what language you're using. Somebody shared the link for RLib actions. You can use R, or most probably if you have some packages, you may use rn, because then you can specify which packages install. But the idea is the same, that you just use something setup R versus setup Python. Okay, so now we want you to all run these actions together with me, just so that you get yourself oriented in the kind of in the whole system. So for that, what you need to do is go to this link where our tutorial is, fork it, and make sure that you get your name here. And once you fork it, you have to do a step to enable running GitHub Actions for your fork repository. The idea is that you run things in your fork so that you have full power of everything, but you will be running all this workflow that I have. So make sure you find the fork button, fork it, and make sure you give permissions through these actions. Allow all actions and reusable workflows. That, I don't know, that may be not entirely secure, but for now it's good enough. I think you can limit it to only ones you care about from your organization, but I think if you do this, it should work. Yeah, that's what you need to do. And maybe once you're done with this, you can use a, let me see which icon you can use for that. Is there like a, sorry. Trying to get to the, okay, here's participants. Can you do, I think there used to be some thumbs up or green thing. I forget now. Can somebody help me? What was the option to specify that you're ready? Okay, thumbs up. Thank you. Yeah, let us know when you're ready, and then we can dive in with the actual workflows. Thank you for the comment. I was trying to understand why things are disappearing.
I think only hand raise actually stays up.
Somehow I don't see the hand raise. Where did it go? Or maybe I'm missing something. Can you folks hand raise? Oh yeah, somebody hand raise. Anyway, indicate one way or another that you're done. How are people doing? Do people need more time? We kind of want everybody to do this step so that you actually do stuff. It's good to try out things. Do people feel they need more time?
I'd say you should probably go ahead.
Yeah.
At least half are already said they're good.
Okay, so let's go. And if needed, go back to the slide and basically make sure that you enable the actions, because otherwise nothing will work. Okay, so let me first run, I'll first run myself, and then you run things, and you basically, I want you to fiddle with the ones that we have so that you kind of try out things. So let's see where we are. So this is the repo that's it's kind of under our organization, so it's Europe eScience. And then, as I said, I wanted everybody to fork it. Here's all the forks people have. My fork, I don't know where my fork is, but I'll just change my username to my username. And so this is my fork. Make sure you have your name here so that you have full power over kind of, you can make edits to the repository. And now that I have that, you can go to this Actions tab here. And you can see I have run some things. You may not have anything that has run. It may be empty here. And you can see there's a bunch of names here. And these names correspond to the different YAML files that we have. The one that I wanted to start with was called Python environment, and it corresponds to Python underscore and that YAML file. Maybe I'll go to it just for a second. So this is the YAML file. And I want to run that. And as I said, that one was set up to have a workflow dispatch. And the workflow dispatch corresponds to having this run workflow button. And we just run it. So click once on it, even though sometimes when you click, it seems like it's not doing anything. It takes a few seconds to register. If you click several times, you'll get several workflows running. See, it takes some time because these are the old ones, like 3 hours ago for me. So, and then you basically start, your workflow starts running. And if I click on it, I can click one more on this setup And here we actually have the steps that we had specified. Basically, the workflow is running through these steps. And you can see for each one, you can see what it actually did. It basically set up Python, right? That was the first thing we wanted. And then, I don't know, I guess these both are setting up. Or maybe just doing some preparation here. And then it's setting up Python. And then it's installing the dependencies. As we mentioned that we wanted to install these two packages. And this is really just like a command. So it's just running through and it's installing things as you do it on the terminal. And then we had hello world, and it's just we're printing the versions of the packages just to make sure that we have installed Python, Matplotlib, NumPy. I guess we installed SciPy or NumPy. I don't know. Doesn't matter. Some packages. And then we finished. This was pretty short workflow, but the idea is to show how you set up your environment. And yeah, and I think that's kind of the main thing, is to go for these actions. And then on the left-hand side, find the action you're interested in. And sometimes you can use this option to rerun this job. But if you really want to make sure everything is up to date, it's better to go backwards and run from here, because then you're going to have the newest version. You're going to get a new version, a new row in this sequence. So I want you all to either run this one, or we had a conda environment too, and edit something in this YAML file. And there are several things that you can edit. You can edit the starting kind of the event on which you run it. As I said, it's run workflow, which means workflow dispatch. But you can edit to make it on push, and you can test by pushing something. Let me get to it. So here it's workflow dispatch, but you can change that and try some other options. You can change some libraries. If you are using actually Python in your research and you have a library that is, you always use it every day, try to see if you can install it and see how long it takes and things like that. Is it easy to install, or it's not easy to install? So try a few options and run it, and just kind of make sure you can monitor the run so that you basically see where things are. So I'll give you some minutes to fiddle with that. And if you feel like you're happy, again, you can either raise your hand or, well, I guess maybe we do the same thing like before. When happy, like with themselves. Okay, so play a little bit just so that you get a sense of it. If you're using another language, change the language. You have to Google the command to change the language. And for those that are happy, maybe you can share if there are some libraries in your field that you tried installing. I'm just curious. What are the things that give you trouble in your field? Did SunPy work if installing through the GitHub Actions? Or it's hard? Is it hard to install or easy?
Started typing, but I thought I would just mention it, just unmute myself.
Yeah,
Answer this
sure.
question. I'll answer with something that is really helpful for installing things that are hard to install. So I work with R, and a lot of the researchers I work with work in R, and R packages that have system dependencies. There's no like rules as to how they declare that. There's just this like plain text field in the description file. But somebody has done the work to match like regular expressions to detect those things in the description with actual like Linux commands to install the needed system dependencies. So that things on GitHub Actions like tend to like just work miraculously with the like the different options for installing R packages, which is really nice.
Yeah, thanks for sharing. That's kind of where I see the value is that it's pretty standardized. So if somebody else has tried to do it, it's gonna work for us too, as opposed to us trying to do it on our own system. Of course, there's other ways to do this with Docker and so on, but it is nice.
Yeah.
And also the versions, we can play with different versions of R, which I think if we try to do it in our studio, we can start messing up a lot of things. So I think there are these things that force us to straighten our workflow. Thanks. Okay. ISCE. I don't know what
in
what
our
is doing.
scientific computing environment. It was a terrible
okay.
of many different kinds of things, and it was really hard to. It took like a full day to try to install it before like a couple years ago.
Yeah, I feel you. I've gone through some other stuff like that. Yeah, I think things are getting easier and these tools are helping us. Okay, so let's dive into one example that also had a lot of trouble with packaging and stuff, but we're getting there, kind of things getting improved. Sorry. Here we go. So this is our example where we're gonna go through the streaming scenario in which we have this, basically, this is the map around Puget Sound, which is sort of like the sound of around Seattle area, and we have these hydrophones collecting data 24/7, lots of data. You can listen to it online if you want to, but we wanted to process the data and share the noise levels with the public. So this kind of with the goal that we understand the environment, the ship noise, and the presence of orcas in the area. So this started as a Google Summer of Code project long time ago, and we didn't have money, so we're like wondering if there's some smart way we can do that. And later other people worked on this project. So as usual, I think I use this example as I call it a typical scientific data pipeline. And what does a scientific data pipeline have? Well, in many cases, I think you have to access the data, process the data, and maybe visualize some data. And access the data is, well, maybe we'll spend most of the time getting like, kind of access and process, maybe we'll spend a lot of time in that step, despite doesn't sound like we're doing anything scientific for that. And partially because the data is messy. In this example, nicely the data is on AWS, but that doesn't make things easier because it's streaming data, it's coming into these 10-second segments. They come in this streaming format, .ts, which is not used by many libraries. And that's why we need to massage this data and convert it to a WAV format. So this is audio data, just to be clear. But the TS format is not popular. WAV format is, WAV format is popular, but there's a lot of work to stitch those together and actually have a time series, as you know, with any sort of data processing task. And then once we have that, we can actually use some other libraries to generate a spectrogram of the data, and we can see the patterns in the spectrogram. And based on the patterns, we can see if there's like a ship or there is like an orca call. So that's kind of our use case. And I'll get a little bit more how we how we set it up to work with GitHub Actions. So we have this noise processing YAML file in the GitHub workflows. And it kind of has more steps, but I'll first explain the steps, and you can just get an idea of how the workflow works. So first, we'll have to install some sound processing library. As I said, every field has its own libraries that cause troubles. Sound is particularly, it has its own troubles. And then we want to generate a spectrogram for a specific period of time. And then we can maybe display that spectrogram. So for that, we have a noise processing.py file. So the idea is that you have a script that is doing some steps. So the steps are download the data from S3, convert all these small files to a WAV format, which is more common in the community. Generate these spectrograms, which you can think of them as, sorry, I don't have the labels, but this is time and this is frequency. So you can think of them as tables. So we can store them in Parquet format so that it's efficient to manage them. And we can read those again with something like Pandas, which is more like a data frame library, something domain agnostic. Generate plots, and kind of in the end, we may want to upload these plots on GitHub. So that's the idea, like, can we do that? Yes, we can. And let me just kind of show you a little bit how the configuration looks like. And so you get a sense of the steps of a more complex pipeline than just installing Python package. So here we have, again, we have workflow dispatch, but in a little bit, you'll change it to something else. We're setting up Python. And as you see here, maybe I'll make this bigger. I'm having this old version of Python, which is the typical thing with a workflow. At some point, you pin it to the versions you use it, and you don't want to change it anymore, which is not very good, but it is working. And we kind of GitHub Actions allows us to have this pinned version to help us out. Then we install some Python dependencies, which is we have put in this requirements _noise text file. And we are installing also this package, which is an example of the ones that you folks are mentioning. ffmpeg is a command line tool that's kind of like a power horse for signal processing. It can convert almost any format to any format. You can convert audio and video. So it's very powerful. A hassle to install. It's become better, but it's still nice if it's kind of easy to install. And in this case, you can install it directly from with apt-get command, but it often causes trouble no matter what. So one of the advantages is that somebody has built this option to just set up ffmpeg, and we can just use it. So that's the power of the community. If somebody else struggled with it, we can actually use it. Later, so as we said, we're gonna run the script. It doesn't matter what the script is doing, it's just doing this processing to generate these spectrogram files. And as I said, in the end, we want to upload, it generates some PNGs, and the neat part is that we can upload them directly to GitHub with this git auto commit action. So I'll stop here and I'll just run this through, and it's gonna take a long time to run, so I'll start it, and I'll just start it so that it gets going. And in the meantime, we can discuss a few other things. So let me just start it. Okay, I need to be on my fork. And you can start the same thing because it's already set up. You can start the same thing running so that you can look through the output. So this one I called ambient sound processing. And I can run workflow, and I'll just run the workflow here. And it's gonna take some time. So this is an example of a workflow that's gonna take a long time to run, and there's gonna be lots of output. But the good thing is that this monitoring option will allow us to see what's going on. And as you can see, it is really installing lots of stuff. It's to set up CPython. There's a lot of packages that are in not the kind of like, they're kind of community built packages. So they're installed directly from GitHub. So anyway, so that's the idea, that you're gonna have lots of installation here going on. And then the goal is to also read lots of data and process all that data. And I just want to say that with this kind of approach, you can process like, I think we could process, I don't think we hit the limit particularly, but we were fine processing like 6 hours of data, which is quite a lot. Like, I think it's like 4,000 files. So I'm pointing this out that because, I mean, you can process quite a lot of data with these 3 actions. This is signal processing. It requires conversion of types, compression, decompression. We're not even using GPUs, but it's working pretty well. So anyway, that's the point, that just that you can do more powerful stuff. So in the end, as I mentioned, the idea is that once you run this, you actually get things uploaded. directly to the GitHub, which is kind of interesting. And I think that was our motivation. It's like, yes, we can process things on our computers, but how can we expose the outputs to everybody? And I think this is some sort of ship going through. This is from the previous run, but we will rerun it and it will get re-updated. Okay, so this is the workflow, and I want you to, so I ran it, and the way it was running with this manual dispatch option. But as I mentioned to you, we can use scheduling. And this scenario is where you kind of maybe want to schedule it, right? You may want to schedule it, let's run every day, or let's run every 6 hours. I actually schedule this for, at some point, let me see, I can show you. I let it run for some time right here on my window there. I have another versions, maybe here. Let me see if I can find it. Okay, I know how to show you. So you believe me. I'll show you from my profile. At some point, I ran it continuously, generating every, what was it, like every 4 hours, I was generating a plot or something. And as you can see from my the GitHub thread, I didn't do all these commits all the time because I'm not spending all my time developing code. But it was actually running continuously, and it was generating all these plots, and we didn't have any problem. It was never cut us out or anything. So that's kind of an example where you actually set up a continuous workflow generating new plots. Okay, so I want you to try and change the existing YAML file, noise processing YAML file. And I want you to go through one example in which you set up the cron job. And let's set up the cron job to run. Okay, we'll have to do the math here. So let's say everybody has a different time zone. I'll write here my time zone. So I'm in Pacific time. And I want you to change it. Let's say that we want it to run in like 5 minutes, which means here for me, it's going to be 3:20. And the schedule of the cron jobs in UTC. So in this case, I need to convert it to UTC, which is going to be 10:20 p.m. And I want you to run it on October 7th. So you'll have to change the cron job schedule so that it actually runs like in a few minutes, and then you'll see if it runs. So try to do that. I won't tell you what exactly the command is. And I may mess up something with the math, but you should make sure that it's correct. The time zone is correct so that you can run it and you see it running with the cron job. So that's the idea, so that you basically see how we can set it up. I guess in this case, I'm saying to run it on October 7, but the idea is you can set it up to run every day or something like that. But I don't want you to set it up to run every day. And if you're finished with that, you can mess something more with it. In fact, you can mess with this noise processing file, and you can change the name of the hydrophone. Or if you know Python, you'll be able to figure out how to change the window. So if you finish quickly, you can mess a little bit more. But the main thing is to run it with a different schedule. So try that, and I hope you can run something in a few minutes. And maybe, yeah, I'll wait a little bit and then I'll try running it with the new schedule too. Did folks see the run happen or not right away? I know that's not entirely responsive sometimes. Did anybody manage to see the new workflow running at a fixed schedule? Okay, who wants to help me with filling this out? Let's say I wanted to run in 26 in 2 minutes. Anybody want to help me how to fill the cron rule?
First thing's 26.
26.
Feel
Okay.
confident about that one.
Okay, so that's the minute. Then the next thing is the time zone mass, which sometimes I confuse it too. So what should I put there? It should be UTC time.
And in 24-hour time, right? So it's
Yeah, good
22,
point.
22 now,
22.
right?
Okay,
I think.
I think so too. Okay, so that would be, here it's 3 o'clock. I know it's different for others. Here it's 3:25 plus 7 should be 10, which is 22. Okay, then what else? Let's see. What's the next thing?
Next is the day,
The day.
which is 7.
7, let's fix it. And then
And then we need the month,
the month. Okay,
which you can either do as 10 or OCT, I think. But 10 works.
10. And then the day, what's the last thing?
The last thing is the day of the week, which we don't want to specify, I think. So
Okay, yeah. Let's fix it just to a day so we don't start running too many jobs. I hope that's the right one where it's already 26. I'll change it to 20. Oh, here we go. Runs and tutor on the day 7th of the month, only in October.
that's nice.
Run at
I
most
did not.
every 5 using. So they are not precise. So that's one thing to remind us that we can't get real time, but that's okay. Yeah, that's nice. Seems like it's right, but let's make it 27 because we're already behind on time. Okay. And I'll just commit this change to schedule. And I'll let it run because, you know, these things are slower. So maybe we'll come back to it and revisit if it ran fine. But that's the idea, that you can schedule those. I mean, you can schedule it pretty often. And I had actually set it up to use a little bit older data, like 1 hour of older data, just because we had some issues with the data. So we won't pull the latest data, just as a disclaimer. But in theory, you should be able to pull the latest data. I'll leave this run. Maybe we can use the time to take the break. And when we come back, we'll talk a little bit more about how to store different options, how to store the results, and a few kind of useful hints. And then we'll dive into large-scale data processing. So let's take a break and come back at well, now we should talk UTC time so we don't get confused, but let's come back in 30 minutes. Hello, everybody. welcome back. So the plan is to go through a few different ways that we can store results, and after that, we'll dive into handling bigger data sets, which even this data set is not small, but we're not doing anything specific to address that. Okay, so the workflow, I looked at it and it was not running. And I think that my problem was that I was missing a space, and I changed that. But I haven't yet seen whether that took an effect. So I hope that fixes it, but I don't know yet. So I'm curious if other people managed to, sorry, this is the, noise processing.
Mine did run.
Okay, so somebody's ran. I had kind of one space here, and now I have two spaces. And I think these things matter. So I'll leave it to wait a little bit, and we can revisit it after that. But it's good at least one ran. I hope you got the idea that with this approach, you can basically set up a kind of real stream processing up to 5-minute precision. And let's kind of just show what this workflow did. I had a one that I had run earlier, but the interesting part is that once the workflow ran, let me get to this. It generated this broadband image,
Valentina,
which is
do you
just
want
summary.
to start sharing again?
Oh, sorry, I'm not sharing.
No worries.
Thank you. I forgot. Okay. Let's go back. So just kind of as an overview, what this workflow is doing is once it was run, in this image folder, it generated this broadband PNG plot, which kind of says something about the noise levels. And that plot we can visualize directly on the README file. So that's kind of the idea of this workflow. So in this case, we directly put the outputs of the workflow on GitHub. As you know, if we have big data sets, that is not a good idea. If we have one plot, it's okay. Nobody complained from GitHub, even when we ran it, as I showed you, we ran it for several months. So that was not a big problem, but in general, you know that may not be the best option if you have a lot of plots. On the bright side, with this approach, you can display the results publicly, and you don't really need to build any dashboards or anything like that. You can basically have the latest plot update and displayed through the README file. So that's that was the idea of this workflow. So let's go back to the slides and discuss how we can store the results. In our workflow, we use this git auto commit up action, which once the PNG file was generated, it was directly committed to GitHub, and you can use any sort of file pattern. So that's one way. Another way is to use what GitHub has. It's called artifacts, which in this case, you store the outputs in sort of the GitHub system, which storage system. And this can allow you to store more stuff and be more flexible. If you don't want to put things on the GitHub right away, you can store them there and then export them some in in a different way. Another way is to store things is to really cache them. And basically, you can reuse them in the future or between jobs. And a third option that is not really a GitHub Action specific option, but more what we as workflow developers could do is we can just push the data somewhere else. Basically, our commands on GitHub can directly upload the results to some cloud storage or Google Drive or even some of our own servers. So these are the few ways. So let's discuss a few of the details. So for caching, what can we store? Well, we talk about storing the plots, but can we store the actual installation setup so that we can reuse it? You could see that these workflows can take quite a lot of time to run. Basically every time it starts from setting up, Ubuntu and installing everything. All these packages take time to install. So we can actually cache that and we can reuse it in the future runs. And by default, whatever got cached gets removed after 7 days, if not accessed. And you have up to 10 gigabytes of cache. So for example, we can go to our workflow here and we can see these kind of, if I scroll down, we can see caches. And well, I thought I should have, not sure why it's not showing up. Maybe I didn't cache it. Well, I guess from the previous example, I had it cached. Maybe I can show you in this example. So let's see. They may have removed those. So I should go to actions. Caches. Here I have some cache stored. So I guess some apt packages that I ran earlier. So here you can find your caches, and it could be the Conda setup, could be the Python setup, or could be something else. There are several ways that you can cache things. So one of them is particularly if we're using pip commands for installation of packages, we can specify cache pip. So this is command from, it's provided. And then we can specify the dependency path of the packages that we want to cache. So in this case, we're installing things from this requirements _ noise, and we can cache everything from this setup, and we'll reuse it. So next time we don't have to run all these commands. And if you're using Conda, similar thing, they actually have an extra command. So this is part of the setup Python action. They have this extra option to cache the pip dependencies. As part of the mini Conda action, you have the option to cache what you install from the environment file. So these are very useful because you don't want to start every time from scratch, especially if you're testing. You may want to reuse some of it. Of course, if you want to start from clean, then you can simply delete this cache. And actually, I think in this setup, I didn't really have them. I have them commented out, but one can make the change and start caching things. So by default, I had these commented out, but I can change it. And most probably I'll mess up some spacing when I'm doing this. I think it should be 2 spaces. Let's look at this example. No spaces. So that's the thing with config files. They really care about the spaces. And it's very easy to do it wrong. Okay, so I can add this And yeah, so I can run this with this change. And we don't have to wait. It takes some time. We can revisit after that. But I'll just run it. And I think that would generate most probably the cache. Okay, so pretty easy with package dependencies to get cached. What else can we cache? We can cache the apt-get install. So that's different from pip, right? That's not Python specific. I mentioned to you this package ffmpeg. It's an apt-get install, and there's an option to actually cache the installation of it. It's by some user, so it's not a community. It's not a GitHub action by GitHub, but people have figured out that would be great if we can cache this. So basically, we can cache packages, apt-get packages, using this action, and we just specify the name. Another way to do it is to actually use a cache function, which that is coming from GitHub. So if you see, as I said, if you see actions that's coming from GitHub, this is from my users. And then you can specify the path of what you want to cache. And in this case, maybe we want to cache the images, right? Maybe we don't want to, maybe we're testing something else and we want to keep the image folder. So in a way, you can specify a folder name of what you want to cache. So that's kind of the idea, that you have different options, whether you want to cache packages or you actually want to cache the actual results, which starts to look like, oh, we're storing the results between the runs. And here there's the GitHub documentation of how you can, like all sorts of options of how you can cache things. Okay, so I uncommented that and I let it run. We can revisit after that. You don't have to kind of run it right now, but I think you get the idea that you can use these extra commands to cache the dependency. Okay, so what other ways to store results? As I said, the other way is to store them as artifacts. So artifacts are basically anything you can store. In this case, again, let's say we want to store the PNG files, but you can store anything that you have generated during the workflow. And you can use this upload artifact action, and it will store it within the GitHub space. It's great because you can store many artifacts and it stays for longer. The caching was only 7 days, while these artifacts can get retained for 90 days in a public repo. So that's pretty much, you can store your results there. And the bad thing is that the format is zipped. So, if you may have to unzip it after that. And it's not ideal if you want to have your data in a very good format. It puts everything together, but it's okay. So where can you find your artifacts? There is basically, once you run a workflow, you can find an artifact section in the workflow monitoring section. And basically you can see ambient sound plots and you can click on it. So let me show you how this looks on the GitHub Actions. So first, let's see if we have an artifact upload. Here we have a section in which we are taking everything from this sound, from this folder, and we are uploading it as artifact. So this was already running. So it should have generated an artifact, and the name of the artifact should be ambient sound plots. Let's see if we can find it here. So I'm puzzled because my schedule flow is still not running. But anyway, we have the older run. I don't know why mine didn't run. In any case, we can see here we had a step in which we uploaded things as an artifact, and it gives us some SHA link to the artifact. But the nice thing is that I think if we zoom out, sorry, no, let's do it this way. If you scroll down, you can see artifact section, and you basically can click on this and literally download this folder, and it was zipped, but my computer unzipped it right away. And I get my broadband plot and my spectrogram plot. And this seems to be some ship coming by. Okay, so you get an idea that anything you want to store, you can, but and you can store here and you can keep it here, but you can also download it. What other ways to download this thing apart from clicking on it, which doesn't seem very programmatic? They actually provide this link, as you can see here, this number, like there actually is a URL link. And again, it downloads it from the URL link. So each one has a link with some numbers. So the good thing is you'll have a link to your data publicly. You can access it. So it's kind of nice. It's not ideal, but it's free. And another option is to use the GitHub client, in which you can run a command from the command line and do git run download and specify the name of your workflow. So that's a little bit more programmatic. And a third way is to use the download artifact action. The problem is that it only works between jobs within a workflow. But once the workflow is finished, you have to use all these other options. So you can use it, across workflows. So these are some way to get our data, basically, if we generate some results, we can access them somehow. So I think in our case, I already had it uncommented. So we have generated the artifacts and we can find them. So we don't have to do this exercise, but I think everybody got an idea of how they can store the results. And here there's an exercise and you can look at it later on, in which the idea is to start generating files for each date. So then you can start storing the whole sequence of spectrograms, for example. Okay, so some comments online. So the question is whether they get overwritten. Actually, they don't. So you can actually keep them, and you can name them differently. If you could see here, we named it. Sorry. Oh, the scheduled thing run now. That's so weird. Unless, yeah, that is weird, but that's okay. At least it's running now. Okay. So as we can see in this example, if we look at the specification here, so in the artifact section, we name it with these ambient sound plots. So if I run it again, and if I name it, it's attached to the workflow. So you can revisit that in that workflow. But the interesting thing is that if you have, you can make this name to actually use the date or something like that. And I think that was the idea of the exercise. So you can generate one with a date attached to it. So then you can actually start storing a whole sequence of data, right? Like you can process big data sets. So I think that's one of the idea. In the real-time case, you can override it, but in the maybe if you want to store kind of large data processing, you can change those. And you can see most probably in Quinn's example how we can organize those. Okay, so this is about artifacts. And the other option is just that I think it's pretty practical, is that let's not deal with all these GitHub stuff because they limit us how we store things. And yeah, maybe I just want my data out. And one of the scenarios that we thought it would be useful for us, folks who just maybe we have some storage somewhere else, and maybe we just want to upload the results there. No problem doing that because we can run any sort of basically any commands on the command line we can run, so we can pass data from the running workflow to some place where we can store the data. And in this case, we thought, oh, I can put my plot on Google Drive. And in order to do that, we use rclone. And rclone is a good example because it's a tool that's very powerful to move data between any one place to another place. It could be Google Drive, it could be cloud storage, it could be some other platform. So it works with a lot of different storage platforms. So we thought it's good if we show you folks how to set up rclone. Because once you have rclone, you can use either Google Drive, but you can use whatever free service you have. Or if you don't have free service, that's okay. You can maybe upload to the cloud storage, and it's not too expensive. So to set up rclone, you normally have this configuration file. It's a kind of command line tool. And in order to do it, of course, we want to check, instead of installing, we can install rclone from scratch, right? But we can check if somebody set up an action for it. And in this case, we checked and nobody had there wasn't an rclone official action, but then there is a setup rclone action by this person, Anima Mouse. And I checked it and there is a discussion, people discussing which action should be official. So sounded like folks like that function, that action. So in a sense, it's good to check if people have trust in these actions before you start running them, because who knows what they're doing. But in this case, I checked it. It looked like people have used it and were happy with it. And then the important thing is, for this scenario, if you try to put to some private storage, you have to give your credentials to these actions. So that sounds a little bit dangerous. That's why I'm saying it's good to check things. But of course, GitHub Actions have realized that we would need sooner or later some credentials. So for that, I can show you where those get set up. And so if I come here and I go to settings and I have secrets and variables and I go to actions. So secrets, variables. So I set up basically this rclone configuration. So it's a secret in which I put my, basically, I followed the instructions actually. They said that I should convert this rclone configuration file, which I already had on my system, into base64. So I did that step on my computer, and that gave me like a long string of characters. And I pasted that long string of characters into this variable. So the idea is that if you want to provide AWS credentials, you most probably can provide AWS credentials. You want to provide some other credentials, it all goes through these secrets. So it is a safe way to upload your data somewhere else. So yeah, that's kind of the last example of how one can set this up. And of course, you know, if you want to set this up, you have to spend a little bit of time of doing the configuration. I had it, and the plot got uploaded to Google Drive. So it's pretty easy once you get the idea. And you can see that once basically when you want to run our clone, you run the actual our clone command, which basically says copy this thing to somewhere else. And it showed up in my drive in our clone uploads in a folder. So that's the idea. Okay, so I think that's all about the different ways of storing things. Of course, there may be other ways you can, but I think that covers a lot of scenarios to get people started and do whatever they need. I'll ask do people have some questions kind of up to here on general caching, storing, running things? I'll stop sharing while you may think of a question. And I'll give the power to Quinn to talk about scaling workflows. And I'll mute myself.
Everybody see this okay? Okay, excellent. Cool. So now we're gonna put some of this stuff together to look at what it might involve to run a more complicated or computationally intensive workflow. And so just generally thinking about scaling these workflows, right now we've just been running a bunch of steps in sequence on a single runner. And the next step might be to try to run some steps in parallel on a single runner, but in practice with the free runners, they're pretty small. They have 4 cores. So one thing that it's actually nice to do is be able to run steps in parallel on multiple runners, which is something that's actually pretty easy to do. And GitHub Actions actually has some features that make it kind of attractive for approachable and light batch computing, including you don't have to put down a personal credit card or any kind of blanket purchase order, which is nice because, I have like nightmares about running up some huge tab doing something that I don't mean to be doing. But you can start for free and then you can pay later on when you want to scale things. They also scale to 0 and the costs are bounded by default. So again, it's like not easy to spend money that you don't mean to be spending. You don't have to deal with like cloud service provider web consoles, which I personally find a little bit confusing and intimidating. It's super easy to share any of these workflows with anyone. They can just, as you guys have seen, fork your repo and they can start running actions. But at the same time, there's this mechanism for keeping secrets secret so that you're not accidentally sharing that stuff. You have this nice dashboard that lets you track stuff as it's happening. And also you have logs for all of your workflow runs, so you can direct someone to an actual run that you did very easily. And you can rerun failed workflows very easily. If you have like a network error, something doesn't download right, you can just rerun it. So those things actually make it kind of nice to deal with for certain like batch processing applications. So some of the other things that we need to sort of think about in order to start developing more complicated workflows. We've been talking a little bit about jobs, but just to explicitly talk about jobs, each workflow contains one or more of these jobs, and the jobs contain steps. And by default, these jobs that we're running, they don't have any dependencies. So if you just have 6 jobs within a single workflow, they'll execute in parallel across multiple runners. And you can specify runner types separately for each job, which is actually kind of cool. I will invite you to post in the chat why it might be neat to have like different runners for different jobs, depending on what you want to do, because I think there's a few reasons that you might want to do that. But if you do want to have some jobs run after other jobs, you can use this needs syntax and you can just specify the order that jobs run in. So for example, in this example here, in this image here, we have job 1, 2, and 3. You can just say job 2 needs job 1, and it won't execute until job 1 is finished. So you can sort of control what order things happen in this way. And sort of to build on that idea, you can also have workflows that call other workflows. So you can have a single caller workflow, or you can even have like nested workflows that call other workflows. And that's really easy to do. You just create a job that uses a workflow YAML file, and you can call that workflow within another workflow. So that's really handy for like organizing things. If you want to have workflows that can be run independently or called by another workflow, you can sort of start to build up these workflows that do different things and build those into sort of a more complicated pipeline. And GitHub will by default just build you this nice like dependency graph, which you can follow along with as your workflows are running, which helps keep everything organized and nice. You can specify inputs for your workflows. So this might not be something that makes a ton of sense for your average like testing framework. But if you're just trying to do some data processing, there are a lot of nice things about having inputs where you can just specify exactly what parameters you want to do your run with. So GitHub Actions provides a really nice way to do that. Inputs can be provided on workflow call or when a workflow is dispatched independently, and you can choose whether you want it to be Boolean, choice, number, environment, string. It's pretty straightforward to specify those if you just sort of follow a template, and it'll give you a nice little like GUI drop-down menu that lets you edit what inputs you want. For workflows that can be triggered both by calling them and by running them independently, unfortunately, those inputs aren't shared across those two different things, so you have to specify them twice, which is a little bit clunky, but it's just the way it works at the moment. And then the last piece that's going to allow us to really easily distribute computation across a bunch of different runners is called a matrix job. And so the idea here is that we can, using a single matrix job, we can spin out all these other jobs that will all execute in parallel on a bunch of different runners. And the example will help me kind of explain that. So in this picture here, we're specifying, we've got strategy matrix, and then we've got these 3 different versions. Maybe those are like software versions and 2 different OSs. And in this matrix that we're setting up, we're going to have jobs that try every combination of these 2 lists, basically. So we're going to try software version 10 on Ubuntu latest, and then Windows latest, etc. And this is sort of the simplest way to set something like that up. There's also functionality to customize your matrix with like if-then style statements. So you can be like, oh, don't do that one, but do this one, things like that. But these also just end up getting saved as an environment variable that's just a JSON. So you can just make your own, you can edit it directly if you want to. And that's what we end up doing for the example that I'm about to show, is we're basically just building our own matrix to specify which image pairs we want to get run. So diving into this example, this use case, so I'll try to keep the scientific background a little bit limited, even though I could go on forever about this stuff because I've been spending years thinking about it. The general scientific background is that by cross-correlating satellite images acquired at different times, glaciologists can measure the horizontal surface velocity of glaciers. So the idea is you take a satellite picture of a glacier and then you wait some period of time, maybe like a month, you get another satellite picture. The surface of the glacier has moved between those 2 images, and then by cross-correlating them, we can measure the amount that it's actually moved. And there are a lot of good reasons to measure glacier velocity, but one of the really important reasons is that we have a pretty good understanding of glacier dynamics, and we can use the velocity to solve for the thickness of the glacier. And by knowing the thickness of the glacier, we can try to figure out how much water is stored in this glacier if we know the density of the ice. And so we can try to figure out, okay, how much water is available for both water resources purposes, but also how much water is locked away in this ice that could contribute to sea level rise if this glacier were to lose a bunch of mass. So that's the primary reason, or I would say one of the main reasons, that glaciologists are really interested in glacier surface velocity. But it turns out that your individual velocity maps, just from cross-correlating like a single pair of satellite images, are really noisy. So in practice, we actually want to cross-correlate many pairs of satellite images and then take some average, and that will allow us to sort of like understand what is the noise in this measurement, what errors are we getting, things like that, and get a more characteristic glacier velocity. And just to sort of show what we're looking for, these are two GIFs that are time lapses of satellite photos. So they're multiple satellite photos acquired over time. They're false color images. But if you look down in the valleys here and you kind of concentrate on the trunks of these glaciers, and you can kind of see that there's texture there, and there's a lot of interesting things happening. Like there are sort of features that you can track that are moving down valley. And that's what we're actually trying to measure. You'll also notice there's all this like flashing and other stuff happening, especially at the higher elevations. That's all snow. And it is going to be a problem for us trying to measure glacier velocity because it will obscure the features that we're after. So that's one of the reasons that we end up trying to do these big averages to try to cut down on some of the noise caused by things like shadows and snow. And specifically, we're going to look at some Sentinel-2 images. Sentinel-2 is a constellation of satellite imagers, so just their cameras in orbit pointed at Earth, that were launched originally by the European Space Agency in 2015. A single image is about 1 gigabyte, and they have a pixel size of 10 meters. So that's the resolution that we're going to have for our images. And we're just going to use images for now acquired over the Yazgul Glacier in Pakistan, which is 25 kilometers long. So it's quite a large glacier. It's also kind of interesting looking. This is it down here. We're programmatically going to download some summer images where there's not as much snow from AWS. And then we're going to cross-correlate them with this AutoRift software, which is a Jet Propulsion Laboratory software inside a Python script. So really, we're just going to run a Python script to do that correlation. And this is an example of what 2 of those images that we might be trying to cross-correlate look like. So this kind of ribbony looking thing is the glacier that we're going to try to measure the velocity of. And I won't go into like what the correlation actually involves in the interest of time, but just know that it involves a lot of matrix multiplication and in sequence, and it's a very CPU intensive process. So even for small images, it can take a long time because you're trying to find the same feature, which could be anywhere within the next image. So it can take a while. And that's one of the good reasons to try to parallelize it. So how are we going to actually accomplish this? We basically are going to have 3 jobs here in order to get this done. The first job is going to query AWS for appropriate image pairs given the inputs. So we're looking for cloud-free summer months image pairs that are far enough away in time from one another that the glacier will actually have moved between them. And then we're going to set up this matrix JSON that specifies which image pairs we want to cross-correlate. Then our second job is going to call another workflow. And the second job, which uses that workflow, is going to actually perform the cross-correlation. So for a single image pair, it's going to do download the images, and then it's going to perform the cross-correlation, and it's going to upload a velocity map from that image pair as a GitHub artifact. So our matrix job might, have 20, 30 pairs of images that are each going to go out to a separate runner to get cross-correlated. And then our final job here is going to compute some summary statistics. So it's going to download all of those artifacts that we just uploaded. It's going to compute some statistics like median and standard deviation to get to cut down on some of the noise. And then it's going to make a figure and upload that figure as a GitHub artifact. And hopefully that will be like a nice, clean velocity map. And this is sort of a schematic showing sort of how this works, but I guess we'll just go to GitHub and we'll look at that. So we can go to Actions, and the sort of like main caller workflow here is this batch image correlation workflow. So we can just quickly take a look at the YAML file and see what is actually in here. So a lot of this we've seen before, but one thing we haven't seen is these inputs. So for this workflow, we have inputs that are cloud cover, start month, which is the first month of the year to start searching for images, hopefully after a lot of the snow is gone. Stop month, which is the last month of the year to start searching for images before hopefully more snow starts. Number of pairs, so for a given image, how many pairs do we want to use it to make? Like, do we want to do n and n+1 or n and n+2, and basically control how many total pairs we're going to make. And then we have, here are our 3 jobs. So our first job is this S2 search or Sentinel-2 search job that's going to run this, we're going to run this Python script, more or less. We're going to do this sort of setup that we've been doing, and then we're going to run this Python script, which is going to construct our matrix JSON. And then our second job is going to be this matrix job. It needs the Sentinel-2 search job to be finished before it starts. And it's going to basically use that matrix to spin out a bunch of jobs to do all the image cross-correlation on many different runners. And then our last job is going to be this summary statistics job, which is going to be executed after the first 2 are done. And it's just going to run this summary statistics workflow. So I'm going to go ahead and get started and run this thing. It should hopefully take somewhere around, I think it's probably going to take like 10 minutes because we don't have the environment cached at this point. So we'll go to, no, that's not what I wanted. Actions. So you can see that when you hit run workflow here on this batch image correlation, we get this nice like drop down GUI where I can actually put all the inputs in. I'm just going to run the default inputs for now. And refresh this. So now this is going to start running, and this is our dependency graph here. So I'm going to encourage all of you, actually first I'll say, so yeah, this should probably use about 23 different runners, so virtual machines. It's probably going to take about 10 minutes just because we don't have the environment cached. If we did this in sequence on a single machine, it would take more like 48 minutes. So it's definitely nice to be able to do this in parallel. And it's going to create 21 velocity maps that are 30 megabytes each, and then the summary statistics figure. And all of that will be stored as a GitHub artifact. In practice, like for similar workflows to this that I actually am using in my work, all of this stuff is just going to S3. But for now, it's nice to have it just as a GitHub artifact. And yeah, I guess it would be awesome if you all try running this. And I would suggest, instead of just running with the defaults, try changing like the allowed amount of cloud cover, change the stop and start month or the number of pairs formed per image. And just as it executes, I would sort of like follow along and just try to see what it's doing. And if that just sounds really easy for you, you can also try running it in a different location by changing the hard-coded GeoJSON that defines where it's currently running. So I'll paste this like handy little GeoJSON defining tool. Oh, I'm seeing stuff in the chat too. And if you want, you can track down the 2 places where that GeoJSON is defined and change that and try to run it somewhere else. And their odds are very good that it will break because this is a canned example for this one spot, but interesting to try. And then, yeah, in the chat, when you're done running this, you can just post like, what do you see in your figure? Do you see anything interesting? Do you see anything that appears to be broken or what you'd expect or not what you'd expect? And then, yeah, just whether you were able to mess something up or really any reflections that you might have, just so that I know that you're done and getting something. And I'll give people about like, I guess 10 minutes from now-ish to run this. Mine is still downloading the environment, it looks like. you might notice that the pairs that are between years take longer to run than the pairs that are within years. And that's because we're dynamically setting how far away we expect features to be in the next image versus the current image. So if it's way longer between images, then we expect that way more movement has occurred and we have to search a larger space for our features. And if people want more background on like how this has been used pretty recently in a really nice paper, I'll send this too. And as some of these are completed, we can see some of the velocity maps getting uploaded as artifacts.
Hey Quinn, do you have an idea how much time gets eaten up transferring artifacts between jobs with the upload here, download there? In this case, we're not doing it much. I'm just thinking if you had a longer pipeline, you were transferring a lot of data back and forth to the artifact store.
Yeah, that's a good question. For purposes for general like research purposes and the way that I've used this, I typically am not doing a lot of that because I'm making many products and then I'm uploading them to S3 and doing the post-processing somewhere with a big RAM where I can actually like do things with all of the data and store all of the data.
Okay.
But I do think, yeah, you could have, I think I would run into issues pretty quickly of just having the disk be too small on these. I think it's 14 gigabytes to even really do much in terms of like downloading all the things I would actually want outside of sort of a more canned example. And also while you're waiting, you can think about, if you're not already, like how you might use this or something similar to this for something in your own domain. I waste a lot of time staring at mine, waiting for it to finish, and just watching all the logs. Okay, so now all of my pairs are finished and I'm just waiting on the summary, which I think is going to have to download the environment.
Quinn, there is a question for you in the chat.
Ah, cool. Yes, exactly. This is like, it is a fluid dynamics thing. And glacier speed is related in part to the thickness of the glacier, the slope of the surface, basically like the thickness gradient. But you can really think about these things as behaving like fluidly, like a non-Newtonian fluid. So they have all kinds of different stresses that they're responding to in terms of that influence their viscosity and control how fast they move. And the other element of this that's challenging is that they are deforming internally like a fluid, but they're also sliding often along their base. So one big uncertainty in all of this is that if most of their motion is driven by sliding along the base rather than internal deformation, then that makes the velocity that we're observing at the surface less related to the thickness and more related to whatever's happening at the bed. So teasing those things apart is often glossed over and not particularly easy all the time. So I assume people still have this running. I'm gonna charge on through a couple more slides, and then maybe we can revisit where people are at, and people can just whenever post or ask a question or anything. So hopefully that, you know, what you're doing right now and what I just did is a cool example of like what you can do with GitHub runners or GitHub Actions rather, but there are obviously also some limitations to this, and it's not perfect for every like batch computing use case that you might have. So I think it's good to talk about some of the like hard limits on this and the limits that you can change with money. So one of those is the concurrent runner limit, and that depends on your GitHub plan. So that's how many machines you can have working at the same time. So if you're on a free plan, you're going to have 20 machines. If you are on a paid plan, you can get many more. If you're on an enterprise plan, you get 500, which seems like a lot to me. Students and educators can upgrade to organizations, and there was can upgrade their organizations to team accounts for free. And I think there was some discussion already about that in the chat, but it's pretty straightforward to do, I think. And it's totally worth it if you want to do stuff like this, because you triple your number of runners that you have available. Some more limitations. Your matrix jobs can only generate up to 250 jobs per workflow run. That said, you can have multiple workflow runs happening. So you can have, 4 matrix jobs occurring at the same time, each with 256 jobs attached to them for, a total of like 1,024 or potentially even more. And that's something that we ended up doing for some of the projects that I've worked on. No more than 500 workflow runs can be queued in a 10-second interval by a single repo. That also seems like a limit that I would be hard pressed to hit, but at least with manually triggering things. Maximum workflow duration is 35 days, which seems like a long time. And maximum job duration is 6 hours, which you can actually run into that if you're trying to do something that's taking a really, really long time on your runner. But if you do want more, it's very easy to hook up your Azure subscription and get into the sort of like metered billing world, which we have ended up doing for one of our projects and experimenting with. I did not look at the costs for this relative to the costs for doing this through Azure or AWS directly or whatever, but Scott Henderson, who helped put this together, assured me that it was like pretty competitive, like pretty standard for paying for these kinds of machines and for other batch processing options. So we're working on these 4 vCPU runners, but if you're willing to pay 25 cents per minute, you can get a 64 core runner, which is pretty cool, especially because you can have many of these. And you can also, I think with a Teams account, you actually have access to these GPUs as well. And certainly if you're paying, you can get access to GPUs. So if you had some reason for needing GPUs, you can definitely use this as well. Let's see. Okay, so my job is finished here, or my workflow. So now we have all of these 20-something velocity maps that are stored as artifacts. They're all zip files, and they're all about somewhere between 20 and 30 megabytes. I could download any of these. I can share the link to any of these, which is pretty cool. And also at the very bottom, this is our summary statistics figure that last workflow that we ran generated. I assume nobody's at this point yet, because I started running mine first, and I don't know what kind. I think I have, but hopefully people. Okay, cool, nice.
And mine finished up.
Oh, great. So yeah, I would encourage you to download this summary statistics file and take a look at it, because that's the thing that we just made. And yeah, you can post any reflections, but also I think it's, you know, just to sort of like check in, now that we're done with sort of the like, you know, bigger data processing piece of this, I would invite people to reflect on like, can you actually see yourself using GitHub Actions for, you know, data processing or data cleaning or something like that type of task? Why? Why not? Or also just anything else you need to get off your chest.
This was great. I use GitHub Actions a lot, but less for like researcher facing things. Some of it is. But one of the use cases that I've seen before that was really cool, but I can't remember who did it, was a data validation kind of workflow, where folks could enter data like in the field on an iPad or something like that, which would, update some spreadsheet that somehow triggers, I don't remember if it was, through a pull request or what, but triggers a validation workflow that like edits the README of the GitHub repo to put like some info in there about whether the data is passing the validation or not, as a way of like, hey, you don't have to wait until you get back to your desk and crunch the numbers to figure out that you forgot to measure a tree and subplot C1, right? And then you could just go do it, instead of, go to your car, fill in the data or whatever, push to GitHub, and then as long as you have internet access, and then, see the mistakes earlier on and save you a drive out to your field site or whatever. So that's something that I'm interested in trying to put together, like an example of how one might set that up, as like a kind of motivating example for field researchers to kind of learn something like this, or get me to help them build something like this.
No, that's a really cool idea. And I mean, it feels to me like there are a lot of ideas like that. Like people use GitHub Actions mostly for a pretty specific set of things, but there's a ton of different stuff you could do. And that's like a great example of like there are all kinds of reasons that you might want to use this. And it's actually pretty flexible in that you can do a lot more with it than I think a lot of people realize. So that's part of our motivation for all of this, I think.
Yeah. Question, I guess when you're creating an action, a dot YAML file for one of these actions, are you using some editor that's like aware of the allowed like variables and syntax, or you're just typing it and you've got the documentation open on another page?
The latter, unfortunately.
Yeah.
It would be
Okay.
nice, when some of these YAMLs get longer and more complicated, I make really stupid mistakes with like spaces and commas and, just small syntax errors. But I mean, there may be an editor that would make that easier, but I've not been using it. I've been finding out the hard way.
Same.
We have not tried using our own servers as runners. We did think about it at one point, but never tried it. Are people mostly ready to move on? Have people's workflows finished running? Here, I can type a message. Yeah, it makes sense. The VS Code has that. Are people on the East Coast getting tired yet? Well, I'll stop sharing here. And Valentina, do you want to take us across the finish line?
Sure. Me orient myself. Okay, so the last portion is really to get in what we started talking about, is kind of thinking a little bit of other use cases. It's kind of like how to combine also different portions to build kind of new applications. And I'll start with just revisiting what we did with a scheduled deployment. In that case, we pushed our outputs here. Oh, sorry, where are we? Not here. We had ambient sound analysis. We had some images and we pushed them here, right? And then in our documentation, but you can make this on the README as we talked about it. But in our documentation, we have different sections, and in this section, we read these two files. So in a way, if we can keep an update on the latest noise levels. And I thought that this approach is powerful on its own because we don't have to build dashboards. But people love dashboards, people love websites. And maybe sending this GitHub thing is not something people want to send if it's the stakeholders don't want to see other GitHub stuff. So in this kind of one of the next examples I'll show is how to kind of automatically update a web page after we have generated new data. And it is really just using the pieces that we have with a few extra commands. And this, I think it's good because especially if we want to share our science, maybe in the end, we want to just share the story and the outcomes. And maybe we want to hide everything else. So in this workflow, it's very similar to what we had before, but instead of instead of having these scripts that we had, like the Python script, let's say that somebody's just working in a notebook and they have basically they're using the commands and they generate this plot. And in the notebook, they can set the date and the time we are running this and the interval over which we want to generate this spectrogram. So that's a little bit of the scenario. I'm like just working on my notebook. How can I make my notebook automatically updating things? So the idea is that we can use nb-convert to convert the notebook to HTML. And we can use GitHub Pages, which is also part of GitHub. So the place where you can actually build a web, kind of like host a website. And we can host our updates on GitHub Pages from that notebook. And maybe if we use scheduled deployment, our notebook can update all the time. And so basically the workflow is we start with a notebook, we convert it to HTML, and GitHub Pages takes that HTML and generates a plot. And the nice thing is that we can go beyond a typical notebook in which you'll have a static plot, because we can make the plot interactive if we use some interactive library. And it's gonna be, I mean, it's not gonna be perfectly interactive. Like, you know, if you wanted to use different data, you'll have to rerun it, but you can also automate that process. So in a way, it is almost interactive, and also you can zoom in and zoom out if you use an interactive library. So this is the workflow, and in this case, we made the plots with the Plotly library, but you can use whatever favorite library you have, and you can host that directly on GitHub. So let me go through, just show you the workflow to do that, like the configuration. So let's come here, and we have these actions. Well, let's look at our configuration files. So we have create website spectrogram. Let's just look at it so that we see the steps. So what do we have? We basically have the same things we used to have before for the script, Python, dependencies, things like that, right? But instead of Python script, we are going to run like the notebook, right? So because we're running a notebook in Python, you have to also install ipykernel, and we want to convert the notebook to HTML. So we're gonna install nb-convert. Still, we need all the fancy sound processing libraries and so on. So then we will run this Jupyter nb-convert notebook. So the notebook is actually here. Let me show you the notebook. Plot noise levels. Sorry, it's too big. Okay. That's one of the reasons you may want to serve it to a website, because sometimes if you just want to show it to your colleagues, you can't, because they don't allow you. I think I can do it here, NB viewer. I don't remember, I haven't used it for a while. NB viewer. Let's see if I can please show it. I don't know if this is active. Okay, here's our notebook. So for those who have not used NB Viewer, if GitHub complains about showing big kind of notebooks, sometimes they can be shown in NB Viewer, and some of the visualizations also can show. So anyway, so this is our notebook, but as you see, because it's a notebook that I was just running my files, and it has a lot of stuff, and there's all these outputs that I don't want to show these to some stakeholders in the city, in the port of Seattle, you know, like they don't want to see all this stuff. But I also don't want to build fancy websites, because these are the ship sounds. They have this very specific pattern as they're coming and leaving. So we can talk to the stakeholders, but we want to hide a lot of this stuff. So in order to do that, we'll run a few other commands. Let me go back to our workflow. What else do we have? We have, I want to go to the configuration file. So we convert this notebook to HTML, but we want to hide some of the things so we don't show everything. So create a website spectrogram. So I can do a few extra tricks, and I can, I can convert it to HTML. But I also can hide some of the inputs, and this way I'll only show the outputs, which is the plots. That's kind of the trick. You'll actually hide the code. And then we'll upload the HTML as an artifact. And the idea is that the next step would be the deploying step, which will take that HTML and we'll just serve it to a website. And there is already a deploy pages action in GitHub, which is used for just generally hosting static websites. And we will display basically our HTML to that website. And we'll run this. I think, again, these things take time. But I'll also show you that I think the website gets hosted then. In this case, we do use just this, we'll use our username and the name of our repo. And in this case, I think it's going to be called, what is it called? I think plot noise levels. Let me see. So let me run this. Okay, deploy spectrogram website to GitHub pages. I'll run this and I'll run the workflow. And it may take some time. But in the end, the path is going to be plot noise levels. So I think I ran it earlier. Maybe see if we have an older run, just so that I show. Did I? Maybe not on this one. I think I might have run it on Github eScience. Let me see if I can show you. Okay, I broke it. I think I ran it here earlier before we started. This was on the main organization, our organization website. So we can look at things without waiting for things to run. We can just look again through the steps so we see what it did. So set up Python, install dependencies, install FFmpeg. We still need everything, build a website. So this is the NB convert step. Upload artifact. It takes all the HTML and uploads it into this thing. And then this one's finished. But then there is another step, deploy, right? And the deploy one, setup pages, they have their own pre-cooked thing. They take the artifact and they build a web page. And the web page, let's see if we can get the link right. It's based on this. So in this one was in this organization, IO, and then the name of the repo, and then I think it was plot noise levels. I'm not sure. Okay, I got it right. So that was the name from the name of the notebook. It became from the IPython notebook, it became HTML. So I hid all the messy code so they don't see it. So that's good, because otherwise they'll judge me. And I just have the plots. And the idea is that we can kind of serve, and maybe people can also zoom in. And this was actually run like for 3 hours. And as you can see, these are the ships. And in general, you can even like, I think there's also ferries coming. So, one can watch and see the relative noise and can start to really discussing, the effect of these. And if you have any orcas, you'll also see if they overlap. And in fact, it was interesting during our break, I received a notification that the orcas were on one of the hydrophones, the port 1001. So if one wants to dig backwards, they most probably can pull time when there's actually sounds of orcas together with the ships. But this is kind of the idea, is like, oh, let's share our science and without building fancy dashboards. So that's one idea. And another discussion is a little bit, we have exercise that I have a simplified example and you can try it on your own. It's just called My Figure. And you can take that notebook, not deal with my messy notebook, and just plot your figure and go through the same steps. And there is a create website, My Figure. So you can try your own libraries with that. You can do it later on. And a few other kind of thoughts about how you can build these websites. So in this case, we just use NB-convert, which just took one notebook and generated a website out of it. Jupyter Book is a way to take many notebooks and generate documentation. And some people may have seen it in the context of building documentation for a package. But you can actually make a whole book with updating plots. And that's kind of interesting. So, your book actually can be kind of re-updating the data. So I think it's a good scenario. If you're using R, you can use the same thing with Quarto. And you can also use any other teams. Jekyll teams were the popular ones for GitHub pages. They're kind of working together. Although they're a little bit, some of them are simple to set up. Some of them are harder. You can integrate with other libraries like D3, like more interactive libraries. You can use read the docs. Why not? Just update things through the documentation packages. And you can also set this whole thing with an actual dashboard. So you can make it more interactive. And here there's a few links about how we can convert plotly plots to HTML, or you can take D3 plots and store the data in JSON and CSV formats, and then all of that can get updated. So you can be creative about which libraries you use and where you store them. So here's one more scenario I just want to share, kind of like a use case where, well, what if we want to set up like a system in which we have a bunch of people working together, and each one of them has a different model that they want to apply to this data. And the model is, first I was thinking to do some Orca machine learning model, but to simplify it, where did the plot go? Well, I lost it. But anyway, you saw the plot where we have the peaks. Why not have it just simple based on, some threshold? People can detect how many ships they have detected. And of course, with the thresholds, you get different results based on a different threshold. But maybe that's a way that people can compare different models and report the results. So this is the idea that it's kind of a community approach of sharing results and comparing results and building this kind of benchmark table so that people can collect the results. And we're thinking to do this for our Orca-Sound data because we have a lot of volunteers who want to do something with the data. The data is public, but we don't want to figure out how to deal with with each person's different algorithms. So maybe they just follow the same format and they just submit the final output and we compile it. And for that, we have a workflow that, as you see, you have the spikes, and based on the threshold, you get different results. And we made a workflow in which you can actually pull, every time a person submits a pull request, the workflow will calculate this, how many ships they have detected based on the threshold that is stored in the person's code. So in the pull request, they have the threshold. And we will generate a table, make it a little bit bigger. And the table gets the username, the number of ships, and some actual SHA from the commit of the person who is submitting the pull request. So in this case, we start versioning each of the models. And so we can go back to it and check what people have done. And we also can pull the usernames. This is just me because I was playing with myself. But if other people submit a pull request, they'll get another one. And I just briefly show you that here we talked about all these other ways of starting a workflow. In this case, we'll want a pull request. And there are several options: open, synchronize, edited, reopened. Synchronize is if people make updates, every time it keeps an update, it still triggers something. So people can reuse the same pull request. And you can see here, we can be smart and we can actually use these GitHub events, and we can start getting, oh, I can get the username, I can get something else. So in a sense, we start using the GitHub information and we can put it in a table. And that's more or less that. We had some extra examples that you can look at, but I'll skip them. And I really want you to live with the thoughts of like how else you can use this in your own workflow. And I think somebody mentioned already this example, but I didn't think about the field. I felt like we can check the data, whether it's reasonable, but it would be even cooler if we can do it from the field. But there are a few other examples. You can retrain an algorithm based on some pull request or things like that. And I don't want to take more of your time, but I want to remind you to fill out the survey. And I'll share the link one more time because you may have lost it by now. And I think there are a bunch of comments. But I will really appreciate, I and Quinn and Scott will really appreciate if you fill the survey, because this is the second time we're teaching this tutorial, and we're trying to improve it. And the previous time we taught it, I screwed up the form, so we didn't get any survey responses. So please, please fill out the survey so we can actually improve it this time. Yeah, and I'll stop here, and I can look through the questions, and I can respond to some more questions in the chat.
I'm going to have to run right at 5:30 here, but I just wanted to say thanks to the instructors, because that was really, really informative.
Yeah, thanks for sticking around, especially those who sticked on the East Coast or even in the middle side of the country. And I'll say also, if you have more ideas or you hear from your colleagues more ideas about different use cases, you're very welcome to add an issue to the GitHub of this tutorial, and maybe we can start compiling them, and we can just have a like kind of like a gallery of use cases. I think that can help people come up with new ideas. So if you hear stuff or if you try something yourself, please share. Thank you all. Have a good evening.
Thank you. That was great.
Thank you. This is great. Thank you for the presentation.